Welcome back, ladies and gentlemen, to another episode of Late Night Engineering. I'm your host, and in today's hour-and-a-half session of ASMR, we're going to be talking about space systems. Now, previously we talked a little bit about the design process, breaking down requirements into functions, breaking down requirements into functions, into components. Today we're going to do things in a little bit of a different order. We're going to go completely in reverse. We're going to talk first about the components. Oop, hello there. We're going to talk first a little bit about the components, then we're going to go over the functions of those components, and then we're going to talk about what kind of requirements you might see in those systems. So without further ado, let's dive right in. So first thing we're going to do is we're going to break down a component tree for a hypothetical satellite. So we're going to start off with just a space vehicle. This is a pretty general space vehicle, but the first thing we're going to break it down into is the payload, abbreviated PL here, and then the bus. Now what are these two things, you might ask? Now the best analogy that I can come up with is that the space vehicle is kind of like a car on a highway. Now the bus is kind of like the car. It gets you where you need to go. It controls most of the day-to-day routines of a space vehicle. And a payload is the thing you attach to the car, or the bus in this case. And it's like the driver. It's the one that is doing all the important stuff and is doing what you need the space vehicle to do. And it's ultimately why the space vehicle is there. So your payload, hang on. It performs the mission. That's its job. That's its function. What that mission is, now for Earth-centric satellites, this can be things, it's most often things like communication, or imaging of some sort or another. Now this can be things like weather satellites, where you're taking terrestrial weather data and you're trying to predict where the storms are going to go next, or it could be ground topography imaging data to try and create road maps or topography maps of certain areas. Now communication satellites, that's fairly simple. That's communications relay. So those are things like satellite internet or satellite phones. Or if you've heard of Elon Musk's Starlink, that's like talking about satellite internet networks. So generally speaking, Earth-centric satellites tend to fall into one of those two categories, communication or imaging. Now with scientific satellites, these functions for the payload can be a lot more broad. So these can be things including rovers and landers, along with probes, or asteroid miners. The functions of the payload can be very diverse when it comes to scientific payloads, and often are unique to the problem that they're facing. But for very simple satellites, we're just going to stick with communication and imaging. Now, what does the bus do? Now, the bus it handles day-to-day operations. It handles the day-to-day operations and control of the space vehicle. Now, what do I mean by that? Well, let's break this down a little bit. Okay, so the bus handles things like EPS, or energy and power systems. It handles ADCS, or also known as attitude, direction, and control systems. And I'm going to kind of add an addendum there and just kind of put thrust also on there. They're kind of similar. It also manages, to some degree, depending on the payload that you're using, a little bit of thermal control. It's a little bit of your thermal control systems. And oftentimes, it also handles communications, so COM. Again, depending on what your payload is, if it's a communications satellite, you're going to have a communications payload, so you're going to have a much more powerful antenna, usually a directional antenna that you're going to be using to communicate to ground. Your bus won't necessarily handle that. So let's go into what each of these different subsystems do. So the EPS here it stands for energy and power systems. Now what does the energy and power systems do? Well, largely the energy and power systems its function is to generate, store, distribute, and regulate power. Electrical power, that is. Now, you can do this in a bunch of different ways, but we're going to break them down into each of these categories. So we're going to take a look at what kind of components can generate power, what different components are used to store power, distribute, and regulate power. Now, generate by far has the most options available to you as far as space systems are concerned. So let's go to generate. We want to generate some power on a space vehicle. So you've got a couple of options here. The most common of which would be solar panels. The sun exists and we can use it for power. So solar panels are by far the most common method of generating power. They use photon energy to excite or create a voltage potential within a piece of circuitry, and they usually send that to a battery to store it. Another method of generating power, which is almost unique or most commonly used in satellites, is an RTG. Oh, that's not what it's supposed to do. Is an RTG. What is an RTG? Well, an RTG is a radioisotope thermoelectric generator. And it basically takes advantage of the fact that if you put couplings of two different types of metal, because of their two different conductivities, if you induce a thermal gradient over those that coupling of metal, you also generate a voltage potential in that metal. So basically what it does is it takes this radioisotope and it puts it in a container. You've got your glowing green rock in here. It's giving off all sorts of radiation. And you just kind of surround that with, it's still green. You just kind of surround that with your thermal couplings all the way around. And you thereby generate a voltage potential across those couplings, and you get voltage out. I'll post a link down below if you want to look more into how radioisotope thermoelectric generators work. It's very interesting stuff. And you get voltage out. So RTGs are most commonly used in deep space missions, so things like the Voyager missions, or probes to satellite or Venus or Pluto. Because the farther away you get from the sun, the harder it is to generate electricity via your solar panels. But unfortunately, you kind of need power regardless of where you are. So radioisotope, or I'm just going to say RTGs. RTGs are a great way of generating consistent power regardless of how much sunlight you get. The problem is, is they're radioactive, and they can pose a bit of a danger on the launch pad, so people try not to use them wherever possible, just to avoid the nuclear problems that come with spreading radioactive isotopes all over a launch pad should the payload explode, or should the launch vehicle fail. So RTGs are only used sparingly when absolutely necessary, and often used when with great care. So another way that you can generate power, it's not really power generation, is just, it's still in red. It's just a battery. Well, that's not really power generation. But if your mission's only like 2 or 3 weeks, a month or so, and you're not consuming too much power, you might not need a power generation system on board your space vehicle. It can turn out that you just need a battery, stick that thing on, and it runs out of battery, but you're decommissioning it anyways, and it's going to burn up in the atmosphere. Once it completes its mission, you don't really care. So if you only really need to use a battery, you only really need to use a battery, which kind of also covers how we store electrical power. It's often used as a battery. You can also use capacitors, but they're not really great for long-term storage. And of course, for distribution and regulation, you have a bunch of different options. They're usually covered by electrical panels or electrical circuits, electrical components. And you have a whole host of options to you. Typically, payloads will also have their own power regulation and distribution boards, just to regulate the power to a consistent level to make sure that you're not getting any surges off of the EPS from the bus, especially if you've got very electrically sensitive equipment, or they're operating on a different voltage than what the bus is supplying. You're going to have to step down the voltage. So that's kind of a general of EPS. Now that's a general overview of what kind of components you can see in the EPS. So what kind of requirements might you see on an EPS system? So we're just going to put this here. What kind of requirements might you see? So you can see things like, put that in black. You can see requirements like power generation requirements. So that would come in the form of watts. So how many watts you have to generate. You can also run into power storage requirements. So that would go into amp hours. And the reason why you might want to have power storage requirements is if you're orbiting the Earth and you have very limited power generation, and you're in the shadow of the Earth, and so let's say you're using solar panels and you're in the shadow of the Earth for a certain amount of time in your orbit. You're not going to be generating power during that time, but you want to make sure that your satellite is still functioning, or at least functioning on a minimal level. So you have to be able to store or generate and store enough power to maintain the satellite's operation through the dark side of its orbit. That's kind of something that you might see in a requirement. Maintain operational capability during the dark side of a satellite's orbit. Something like that. Now, of course, I'm going to kind of slap on a general requirement that you see a lot with satellites, and that is reliability and survivability. Now you see this kind of requirement on a lot of different components in a space vehicle, especially since you cannot fix a space vehicle once you have launched it. Once it's in orbit, it's very unlikely that you're going to spend how many millions of dollars to get a person up there to try and fix that thing. Which is why a lot of space systems have redundancy built into them, and they're heavily tested on the ground before they go to space. So if you ever see something like that mentions TRL levels, that's technology readiness levels. I'm just going to kind of put that underneath here. TRL TRL levels are basically just an organized way of labeling different levels of trustworthiness and testing reliability for a component. So different TRL levels can go into how many missions, whether it's flown and successfully been operated in orbit, and it's just basically a history or a legacy behind a certain component or electrical board or circuit. I'll post a link down below on TRL level specifications. If you want to go through that, you can look at all the different what each of the TRL levels mean. So that's kind of a general overview of EPS systems. Next, we're going to move on towards ADCS systems. So ADCS stands for Attitude, Determination, and Control Systems. So what the hell is attitude? Well, we're certainly trying not to program our space vehicle to have an attitude, but we do want to be able to control its attitude. Now, attitude is just generally, or I'm going to put a little arrow here, attitude is just where the spacecraft is pointing. Now, why might it be important to know where you're pointing and to control that? Well, this comes into play with a lot of different systems, especially communications and visual systems. Because if you can't, so let's say you've defined your attitude system. You've got a camera and imaging satellite. You've defined your attitude system to be along the axis of your camera. So that's your attitude. You want to be able to look at things with your camera. If you don't know where you're looking, or you don't know where you want to look, you can't find anything with that camera. So this also comes into play with things like communication systems. If you've got directional antennas or ISL lasers or inter-satellite link lasers, you need to know exactly how your spacecraft is oriented, or space vehicle is oriented, and you want to know how to control your attitude or attitude of a particular component in order to point where you want it to point. So we can also break this down into two different subsystems. Well, we've got the attitude determination part of ADCS. So I'm just going to say you can determine your attitude, and then you can control your attitude. Now there are different kinds of components which do these different functions. So that's its function. Its ADCS function is to determine and control where the space vehicle is pointing, and I will also add it's also determining how fast you can also control how fast your vehicle is rotating about a certain axis or a set of axes. So you can also control your angular velocity or angular acceleration. Those are the symbols omega and alpha, respectively, for angular acceleration and angular velocity. Angular acceleration alpha and angular velocity omega. Now, different components that can be used to determine. There are different components that can be used to determine. There are a lot of different options for determining your attitude. And these can be things. I'm still in green. These can be things like gyroscopes. These can be things like IMUs. You can use star trackers. We can use earth sensors. We can also use sun sensors. And magnetometers. And we're just going to go over a little bit about how each of these work. So first and foremost, just going to erase this for a second. We're going to write them in later. Gyroscopes. So what the hell are gyroscopes? Well, gyroscopes work off of the principle of conservation of angular momentum. Now, what does that mean? Well, that means, that if you set an object to be spinning, as long as you don't have any non-conservative forces acting on that spinning object, it will maintain that axis of rotation that you gave it initially. So if I take, let's say I take a disk, right? And I just give it a good hard spin, and I spin it about its center of mass. It starts spinning with a given angular velocity. Now, in a frictionless environment, it'll keep that vector of rotation. So, using the right-hand rule, we can tell that if it's rotating around counterclockwise, the vector of its rotation is up. So, unless I do something to change the rotation of this disk, whether that be changing the direction of its axial rotation by like slapping it on the side and maybe changing its orientation. So it'd be rotating like that. Or maybe speeding it up, like giving it another good spin and increasing the magnitude of its of its angular velocity. It's going to stay in the same direction, unless I do something to change that. That's pretty much the conservation of angular momentum. Now, down here on Earth, if you spin anything like, say, a spinning top on your desk, or spin a coin, like flick a coin or something like that, eventually it's going to come to a stop, because whether you like it or not, there are going to be non-conservative forces like minor amounts of drag, friction between the table and the top, that are going to be taking energy out of the coin or the top, and eventually it's going to slow down and come to a stop. But in space, not really the case. There's no atmosphere to speak of. And if we put something like a rotating disk in a gimbal, that's not a good gimbal. So gimbal, we have our little rotating disk, and it's spinning in that gimbal. What a gimbal is ostensibly a mechanism that allows for a free range of rotational motion. It's often used in camera work, so whenever you're doing like movies, whenever you're watching movies or something like that, you see a really smooth camera shot. A gimbal is basically removing jitter and mechanically smoothing out the shot to make things easier to see. They're also used in space systems with gyroscopes. Now, what the gimbal does in this case is you have something spinning. Ooh, there goes my charger plug again. You have something spinning in your spacecraft, and you've got it spinning up with a certain vector. So you know that vector. And as long as it keeps spinning, and it has a relatively frictionless environment around it, i.e. a gimbal, we can put it inside of our space vehicle. So say we've got a little CubeSat here. We can put it inside of our CubeSat, and we can change the orientation of our CubeSat however we like, and due to the principle of conservation of angular momentum, that little gyroscope, that little spinning thing in that gimbal, will maintain its vector. It'll maintain the direction that it was spinning in. So if we know, say that's the direction of the gyroscope, or say that's the direction of the gyroscope, we'll mark that with a G. And then we have, we don't go away. Yeah, screw it. And we have our satellite attitude. We can find the angle between these two, and because we know that the gyroscopes, the direction of the gyroscope's rotation is always constant, we can say, alright, well, we were 35 degrees before at time t0, and now we are at 120 degrees. I know these aren't 35 and 120 degrees, but just bear with me. At time t, well, that means we, went through, we changed our attitude a little bit, and we know exactly by how much. We do 120 minus 35 gives us a number, because I don't want to do math today. But that doesn't really give you information about, so that gives you kind of a relative orientation with your gyroscope, but that doesn't give you really a sense of where your spacecraft is pointing in 3D space, which is often why you see gyroscopes come in pairs of 3s or pairs of 4s. So oftentimes you'll have a gyroscope that defines an orthogonal coordinate vector system. So in order to define any three-dimensional space, you can define it with three unique vectors. They don't have to necessarily be orthogonal, but for the purposes of convenience, it's often the case that in any three-axis gyroscope that you use orthogonal vectors, just because it's nice to think about. You don't have to do any rotational math or coordinate transfers. So you have one gyro spinning in that direction, one gyro spinning in that direction, and another gyro spinning that direction, and then we have our vector, our attitude. Let's call this G1, or actually call this GZ, GX, GY, right? And each of these has a particular angle that we know. Oop. Yeah, I don't want to make it green. Make it red. Has a particular angle with our attitude. Now, we know that because we know where each of these gyroscopes is pointing relative to our spacecraft attitude. And if we know that, and we know where our gyroscopes are pointing in a general reference frame, we can then use these angles between our attitude and our individual gyros to determine where we are pointing in 3D where our spacecraft is pointing in 3D space, in whatever coordinate system we want it to be. Now, another configuration you might see some gyroscopes take is a tetrahedral or tetrahedral orientation. That kind of looks like if you've ever played jacks with the bouncing ball and the jacks, or you're a fan of history and know what a calthrop is, those are tetrahedrals. You can also see this often in organic chemistry, so methane, I believe, is in a tetrahedral orientation. So just imagine, so those chemistry people out there, just imagine that as carbon, just hydrogen sticking out the ends. Except in this case, it's not carbon. Those aren't hydrogen. And we're looking at gyroscopes. So you get these gyroscopes in a tetrahedral orientation. They're all like separated by 120 degrees. I think it's 120 degrees. You can look that up. Tetrahedral. Wikipedia that shit. Alright, so why would you often see gyroscopes in tetrahedral orientations? And the reason for that is if one of these goes offline, or you get a failure in one of them, like let's say it just breaks, any of the remaining three, so 1, 2, and 3, still define unique vectors in 3D space, which means you can still use the 3 remaining gyros to determine your attitude, regardless of whichever one of these fails. So let's say it's 1 fails. You've got 2, 3, and 4. If 2 fails, you've got 1, 3, and 4. Etc., etc. You are allowed 1 failure of a gyroscope before you lose any functionality whatsoever. Now there are some clever things you can do with just 2 gyroscopes and integrating any of your other attitude sensors to try and guess what your attitude vector is. But that's for another video. But that's just basically how gyroscopes work. They keep a small spinning object in your spacecraft, and due to conservation of angular momentum, those spinning objects maintain the same rotational vector, which you can then use as a relative map to your satellite vector, which you can determine where you're pointing. If you have 3 of them, you can determine where you're pointing in 3D space. So those are how gyroscopes work. Now, the second one we're going to go to... Oh, come on. Okay. Second one we're going to be talking about are IMUs. Now, IMUs stands for... They stand for internal measurement units. Now, what these do... I'm just going to scroll down if it'll let me. Yes! Alright. So what internal measurement units are is they're just basically a set of accelerometers. They measure the acceleration in a given direction. Now, you'll often see they come in 2 different flavors. They come in rotational or translational accelerometers. So if you have 3 accelerometers, 3 orthogonally set up accelerometers, you can measure your acceleration in the x direction, acceleration in the y direction, acceleration in the z direction. What that'll give you is if you measure that over time, so, come on, I'm getting a little bit of lag here. Alright, so if you measure that in time, so you get AX, AY, AZ, with time. Oh, come on. Wrote time twice. Okay. With time. And you get some pattern, right? Right? You get a different pattern for acceleration on each of these. You can integrate with respect to time, or in this case, double integrate, to get the distance that you traveled with that time. So if you've got a very accurate clock, you can say, okay, we know with very high fidelity the acceleration and the given amount of time in these 2 directions, and we know our initial state being at rest, so we know v at time naught, distance at time naught, and the x, y, and z, and from that, from where you were, and the amount of time that passed, and given that you know where you were, the amount of time that's passed, and your different acceleration curves in the x, y, and z, you can figure out how fast you're moving with respect to time in the x, y, and z, and how far you went in the X, Y, and Z. So those are kind of, that's how you define translational, or that's how IMUs are used to measure translational motion of a space vehicle. But you can also use them. Well, with a space vehicle, it's a little different because you can move without accelerating. That's just kind of the way that orbits work, although you are technically accelerating because you're changing your velocity vector, but I digress. The second and more useful flavor of IMUs are rotational IMUs. That's a bad one. So they are used to measure the acceleration for the roll, or if I'm looking into the paper here, that's a roll. If I'm looking into the paper, that direction is pitch, so pitching up and down. So roll, pitch, and yaw. So roll, pitch, and yaw of your spacecraft, and they do the same thing. So they measure alpha x, alpha y, alpha z, or alpha for the roll, pitch, and yaw respectively. I'm just using x, y, and z because that's easy. And you get a certain pattern over time, and you integrate that, and you can find out your angular acceleration, any change in attitude with respect to time, based on an initial state. So that's basically how IMUs work. The next one we're going to be talking about, I'm going to kind of lump these together, are the star trackers, the Earth sensors, and the solar sensors. Now all of these are visual based. So they are taking imaging data. So they're taking visual data from one source or another and using that to calculate your attitude. Now the way star trackers work is they just create a 3D map of stars around you, and assuming, so I'm just going to say, like, say that's your spacecraft, right? And it creates a sphere with different constellations or different maps of stars around you, and it says, well, I'm looking, oh, there goes my charger again. Well, I'm looking at this constellation, or this constellation is within my field of view in like the bottom right, like corner. So translating that into angular space of the camera's FOV, I can say, well, if I'm looking at this constellation, it's this part of my FOV of this star tracker, I know I'm looking at this point in the sky, right? So it's kind of like if you were on the surface of the Earth, right? And you're just kind of sitting there one night in the field doing some stargazing, and you go like, hey, look at that. It's Orion. I have not. Okay. It's Orion. I think there are two stars here. I can't remember. It's Orion, and you know, hey, that's kind of in that part of the sky, which means that based on the Earth's rotation, I am looking at this part of the sky. So that is my attitude, right? You can determine your attitude based on the map of stars that you're looking at. Now this only really works if the stars are really far away, because it assumes that the stars aren't moving. when in reality they actually are. But the distance between you and the star is so vastly huge that it doesn't really matter if they're moving even a couple billion miles, because they're so far away from you, they're ostensibly staying still. Now, this isn't the case with our next visual-based sensor, and those are solar sensors. That star is a little bit closer, and it's a good thing too because it powers all life on Earth. So solar sensors work by using your current orbit and the knowledge of your current orbit and where the sun is, and going like, well, I know what time of year it is. I know what orbit I'm kind of in, and I know the sun's right over there. So that must mean that I am pointing in this direction. Now there's a whole bunch of math around that, but because the solar system from a finite perspective in time isn't a dynamic system, big caveat there, if we're looking at very short periods in time, we can ostensibly say that everything in the solar system is static, or at least its large bodies are. This isn't true over long periods of time. With regards to larger bodies, solar systems are dynamic, all gravitational bodies are. But we can say that on the short term, within a couple, 100 human lifespans, it's the case. It's more or less going to be the same. And you might get some drift over time, which you can correct for, but it basically works like that. It's saying, like, I know where I am, I know the sun's over there, which means I must be pointing in this direction. That's kind of how solar sensors work. Now, Earth sensors work in very much the same way, except working with a body that's a lot closer, but gives off a lot less light, or at least a lot less visual light. That's an Earth sensor, and it senses the Earth, obviously. Now the thing is if you have an Earth-centric satellite, you might not necessarily see the entire Earth. So you might only see, so we've got our Earth here. And that was terrible. Terrible. So you've got our Earth here, and you've got your satellite orbiting it, right? Now you might not necessarily see the entire, so actually that's a bit too. So let's say you're orbiting from this distance, right? You might not necessarily see the entire Earth, right? You might only just see a portion of it. So what the Earth sensors are there to do is basically to try and determine where you are relative to your nadir vector. Now what a nadir vector is let's just say that's the curvature of the Earth, and that's your satellite. Your nadir vector is the vector that's pointing directly down, i.e. towards the center of your orbit, i.e. the Earth's center, or one of the foci of your orbit, if you're in an elliptical orbit. We'll get into that later. But in this case, the nadir vector is directly towards the Earth's center. And how it does that, how Earth sensors do that, isn't by generally measuring the Earth, because you might not necessarily see the entire Earth, right? You might only just see a portion of it, based on how what your altitude of orbit is. Now, if you're well past geo or something like that, you see a lot of the Earth, but you don't see, like, you see a good circular chunk, but you don't see entire. Actually, if you're at geo, I think you are missing out on a couple degrees. I'd have to do the math again. But basically, the point is if you're far away, you can see more or less the entire Earth. But if you're really close, come on, dealing with that lag again. Ah, there we go. So if you're really close, you're not going to be able to see as much, which means you won't get a perfect circle in your vision. Because if you have a perfect circle, it's really easy to say, oh yeah, that's the circle. You get out your ruler and go, like, that's the center. But if you're close, you can't really do that, because all you see is this, say, like, that's your FOV, and then it's all just black, right? it's entirely covered up by the Earth. But what you can do is you can shift your attitude and look for the Earth horizon. At that point, you can kind of see the curvature through some atmospheric haze here. You can kind of get an idea of the curvature of the Earth, And based on that curvature and your attitude, you can kind of go like, oh, let's draw some tangent lines here. And then, okay, let's take a look at the top here, and that's our horizon from the top of our FOV. Those are all kind of pointing in that direction, so you can kind of like piece together like, oh, all of these are pointing at the same, all of these radial vectors are kind of pointing towards the same center, and you can go like, oh, oh, look, that's my nadir vector. So that's kind of how Earth sensors work, is they just kind of like hunt for the Earth horizon, and they can use the curvature of the Earth to find out where your nadir vector is, and then from that determine where you are pointing relative to that. So star trackers are fairly general. They work regardless of where you are because of how far away stars are, and you can create a map and it's relatively the same. You can create a star map and it's relatively the same regardless of where you are in the solar system, because the stars are, for ostensible purposes, infinitely far away. Sun sensors require a little bit more work. It's more often used on Earth-centric satellites just because the Earth's orbit is extremely well known, and it's very easy to do the math and figure out where the sun is going to be given a certain orbit. Earth sensors, of course, are used almost solely on Earth-centric satellites. Because if you're in orbit around Jupiter, knowing where the Earth is isn't going to help too much. But Earth sensors can be used, or can be used on any planet if you know how big that planet is and what kind of atmospheric interference you might get. So like if you're looking at the horizon, like here, you might get different haze, so it's a little bit harder to pick out where your nadir vector is off of that. But they still can be used. Okay. So that goes over kind of the sensors. Oh, I completely forgot. We also have magnetometers. Jeez. Oh, come on. Okay. I'm just going to start writing. Okay. Magnetometers. So what are magnetometers? Well, magnetometers, fairly simply put, they measure magnetic fields. Now, why is this useful in determining where your space vehicle is pointing? Well, that goes with a little bit of extra information if you know if the body that you're orbiting has a magnetic field. So in the Earth, so let's just draw an Earth here. You have, and we have its center of rotation. I'm just going to make this a little bit more spherical looking. And you have Earth's center of rotation. You've got a north and south pole, which are slightly off from that. So, the Earth's magnetic field is extremely well known. We know exactly what direction these field lines are going in and what their magnitude is. So if we know exactly what direction those field lines are going in at different points in your latitude, so we know at different latitudes and longitudes and altitudes where the field lines are going, exactly at what magnitude those field lines are going in. Oh, let's get rid of my error. We can use that information to determine how we're pointing. So let's say we've got some orbit that passes through the Earth's magnetic field, and you've got a space vehicle that rides along that orbit. If we know right here, if we know where the Earth's magnetic field is pointing, oh, come on, lag, so much lag. If we know roughly where the Earth's magnetic field is pointing at every point in this orbit, we can use the magnetometer data measuring the direction of a magnetic field to control, to determine where we are pointing relative to the Earth's magnetic field. And since we know where the Earth's magnetic field is pointing, we know where our spacecraft is pointing in general coordinate systems. So that's basically how magnetometers work. So yeah, that's kind of good overview of different attitude determination systems. Next we're going to go over is a little bit of controls, or control systems. Alright, so sorry about the change, there were some technical issues, but let's just jump right back into this. So controls and control actuators. So first off, we're going to be talking about some of the more simple methods for control actuation and control of your attitude, and that's spin stabilization. Got something stabilize. Spin stabilization. So what is spin stabilization? Spin stabilization is, well, say you've got your satellite. It works very similarly to how control moment gyros work, where they have something spinning in your spacecraft, and those maintain that they maintain their attitude through the conservation of angular momentum. It's very similar with this, except instead of spinning a gyro, what you're doing is you're spinning the entire craft. So you've got an axis of rotation that you are spinning your entire space vehicle around, right? So you got some angular velocity there. And what that does is, by spinning it in along that axis, you are maintaining that axis regardless of whatever perturbations or stuff you throw at it. Now you can change it slightly, so if you just bump it or something like that, it will change. Also, if you get like hit by a pebble or something like that, like a rock or something like that, it might shift the axis slightly by a certain degree. So it is prone to some change, but in large part, you most likely won't be hitting debris, especially if you've taken care to put your satellite in an orbit where it won't encounter certain disturbances like that. So in large part, if you induce that kind of rotation, it'll maintain that rotation along that axis. So if you had your camera right at the end of one of these axes, and you were looking in that direction, you would maintain that attitude, and you'd be able to, look at whatever's in that direction. Now the downside of this is it's very hard to change this axis in a controlled manner. So if I wanted to shift this or maybe look at something else, it'd be very difficult to with active control systems, which we'll get into in a second. So what you'd have to do normally would be to slow down the rotation in that axis, and then you could actively control it, which isn't very fuel efficient or energy efficient. So typically it's only used if you know you're only going to be looking in one direction. Now I mentioned in my example here that I used a camera, so you'd be able to look in one direction. The problem is that when you're in an orbit, so we're just going to draw the Earth here, and you're in an orbit, right? And you've got a little satellite there. The thing is if you maintain one attitude, so you'd be spinning along that axis, and if you're looking along that axis is going to be maintained regardless of where you are in your orbit. So if you're on the far side, you're going to be looking. If you're on the far, if say you're looking at the Earth, in one part of your orbit, like you're looking directly along your nadir vector, you're looking directly at the center of the Earth. When you get to the opposite side of your orbit, you're going to be doing exactly the opposite. you're going to be looking directly away from the Earth. So you're not going to be looking at the Earth at all points in time along your while you're in your orbit. So if I was here, let's say I'd be still looking along that same vector. If I was here, I'd be looking along that same vector. If I was here, I'd be looking along that same vector. It conserves a vector no matter which part of your orbit you're looking at, which isn't necessarily the best thing if you want to be looking at the Earth at all points in time. So if I wanted to be looking at the Earth at all points in time, let me just redraw the orbit here. What I'd really want is a vector that looks along my nadir vector regardless of where I am, right? So if I was at this point, if I was at point 1, or if I was at point 2 or point 3, I'd be looking at the Earth no matter what. Which means that as you're orbiting, you want to be rotating about an axis perpendicular to the plane of your orbit at the same angular rate that you are making your orbit, right? Which for circular orbits, it turns out that the rotation around your self-axis is going to be constant, which is nice. You can just set a certain constant rotation of your satellite, so as it goes around its orbit, it's constantly looking at the Earth. But if you have something like, so if I'm just going to draw a little circular orbit from overhead, so I can look at the Earth regardless of where I am if I induce some constant angular velocity. But if you have something like an elliptical orbit, you're not going to have the same velocity at all points in your orbit. So you'll be, I'll get into reasons why that is later, but for now just accept that the further away you are, the slower you're going to be moving. So you're going to have at this point, you're going to have a really slow angular rate, and at your perigee, so this is the apogee of your orbit, or the furthest away you're going to be, and here's the perigee, or the closest you are in your orbit, this lowest orbital altitude that you have. At your apogee, you're going to have a very slow angular rate, and at your perigee, you're going to have a really fast angular rate. So you're going to be moving really quickly at your perigee, you're going to be moving really slowly at your apogee. So if I were to be looking at the Earth at all points in my orbit, I would have to slow down my angular rate. Slow down, slow down, slow down. So the rate at which I spin around my own axis would have to slow down, and slow down to the slowest possible point, and then it would have to speed up. So omega plus on this side, omega minus. I'd have to slow down on my way out, and then I'd have to speed up on my way in, right? So that requires more active control, something that spin stabilization just can't do. So something like this is often seen in satellites that have inclined orbits, or that are looking at along polar orbits. That's things like Molniya orbits or tundra orbits and stuff like that have an incline to them. They will often be slightly eccentric because they want to be looking at the North Pole as much as they can. And so that'll be things like there are a lot of satellites that measure greenhouse gases, or that observe ice shelves and stuff like that. They want to be looking at the North Pole as much as possible, and the way they do that is they have eccentric orbits that slow them down while they're looking up at the while they're right above the North Pole or the South Pole, so they can take a really nice long look at the polar ice caps. But spin stabilization doesn't do that because it's going to be looking in the same vector no matter what. So for something like our elliptical example right here, we're going to need more active control, and that'll get into things like thrusters. Thrusters, they come in a lot of different flavors. You can have cold gas thrusters, as well as hot gas or ion thrusters. Now these two are kind of similar. We're going to need more active control, and that'll get into things like thrusters. You can have cold gas thrusters, as well as hot gas or ion thrusters. Now these two are kind of similar. We're going to need more active control, and that'll get into things like thrusters. You can have cold gas thrusters, as well as hot gas or ion thrusters. Now these two are kind of similar. in that they use a pressurized gas or fuel to drive the thrust that they generate. So the way that thrusters work, I'm just gonna talk about cold gas and hot gas right now. I'm just gonna ignore ion thrusters for the moment. The way that thrusters work for actuation control or attitude control, is you typically have a tank or reservoir of compressed gas, and then you have nozzles kind of separated, spaced out along your space vehicle. And they're connected by pipes, and you have different valves along these nozzles. And what you do is you basically just kind of open and close these valves for given amounts of time, allowing the gas to escape. And where there's an action, there's an equal and opposite reaction. So as the gas leaves your nozzles, your space vehicle will be imparted a force in the opposite direction. Now, if you're aware of how moments work, or torque works, let's look at this from above. So you have one nozzle, and you have another nozzle, and you're imparting gas is coming out this way, gas is coming out this way, and your center of mass is here. So if we draw some lines here, and we have some force from each of these nozzles, so F1 and F2, what that does is you have force at a distance from your center of mass, which will cause a moment, or a torque. Just going to give it a little torque symbol. So force at a radius, acting at a radius of your center of mass, will give a torque, or an angular acceleration, based on, so where this, it'll give your space vehicle an angular acceleration based on the moment of inertia about that axis. So this is the moment. And I often like to think about moment of inertia as kind of the rotational mass of an object. So much like force is equal to mass times acceleration, torque is equal to the moment of inertia, or your rotational mass about an axis, and the angular acceleration. So in this case, we're applying a torque, and we are getting an angular acceleration out. So it is starting to speed up about that axis. So we are actually rotating the space vehicle. So that's kind of how cold gas and hot gas thrusters achieve an attitude change. So they're often paired with electronic systems that control the valves on your space vehicle to change your attitude by a certain amount with certain design characteristics into that, and that goes more into control theory and controller design. But for now, let's just keep it simple. Your computer is controlling when to open and close these different valves for your cold gas or hot gas thrusters, and by doing so, they induce a moment about your spacecraft which changes your attitude. And that's how they work. Ion thrusters are a little bit more complicated. They basically work by charging different particles with a certain electric potential and then passing them through an electric field and accelerating them out of your spacecraft. The benefits of this is so they basically just have an electric field kind of moving in this direction, and they just give like a positively charged ion. Usually it's xenon. I'll get into that in a little bit. And they just basically, by having a charged particle in an electric field, they just accelerate that sucker out at ridiculous speeds. The benefits of that is you have very high fuel efficiency. Number one, you're using electricity for thrust, which is a replenishable resource while you're in orbit. So you can kind of recharge your space vehicle. You are using xenon gas though, which isn't replenishable. So eventually it's going to run out. But ion thrusters tend to be very fuel efficient, or in the terms of rocket science, they have a high specific good impulse for very little effort. But the problem is they are accelerating these really small particles really fast speeds, is they don't give your spacecraft a lot of momentum, which means they don't give a lot of maximum thrust. So oftentimes you'll see ion thrusters used over very lengthy periods of time. So you're, instead of giving like 40 million newtons all in the space of like a minute, you're going to use like 1 or 2 newtons over the period of months or years, which is helpful in deep space, where you have that amount of time to shift your orbit so ever so slightly in some directions over long periods of time. Now, ion thrusters are often used for the reasons I just described as main engines, not necessarily for attitude control. Because remember, for attitude control, we might want to be able to slew really quickly, or we might have requirements that say, hey, we've got to point a lot of different objects really quickly, and a low thrust system might, while very fuel efficient, isn't very good at changing our attitudes very quickly. But if you say let's look at the back of our satellite here. Let's say you have like 5 thrusters, right? What you can do to induce a moment about your craft, and you've got your center of mass right here lined up with that central thruster. What you can do is you can say, oh, hey, if you fired these 2 thrusters at the same time, but not the rest of them, what we can do is I'm just going to, so looking at it sideways here, so there's a center of mass, there are 2 thrusters, they have a force, so they're flinging things out the back, they're giving you a force in this direction. What you can do is, hey, that is a little radius, and that's some force. Hey, I'm actually imparting a moment on the spacecraft because it's giving off-axis thrust. So if you want to change your attitude ever so slightly, if you have ion engines or something like that, you can change your attitude a little bit. Now, a larger scale example of this would be something like the shuttle, where you actually do have these massive solid boosters, and then your giant propellant tank of liquid propellant. And then you've got the shuttle. That's a very poor drawing. But you've got your shuttle kind of strapped on the back there. What you can do is you can say, hey, we can kind of use these thrusters to change the attitude of our craft mid-flight. So if we wanted to add a little bit of a tilt for our orbital burn, we can kind of use those thrusters or actuate the direction of the nozzles just ever so slightly to get the orbital burn path that we want when we're leaving the Earth. So when you are burning into an orbit, you're not actually just burning straight up, you're burning to the side, because what you really want is horizontal velocity in order to get enough velocity to achieve an orbit. So what you're doing is you want to burn to the side. And to do that, you want to change your attitude a little bit, and you can use these thrusters to change your attitude ever so slightly. So that's kind of how you can use thrusters for attitude control as well. Now, another one that is more common for smaller satellites is is a magnet torquer, or a series of magnet torquers. Magnet torquers, boom. So magnet torquers are basically just coils of wire. So I'm just going to draw mine as a square here. So magnet torquers are just basically coils of wire. And what they do, actually it behooves me to represent them as a spiral, but I'm just going to represent, just imagine this as just kind of like a big loop of wire that we've wrapped around a bunch of times, right? How magnet torquers work is they just induce a magnetic field. And you might be thinking, well, how does that actually change your attitude. So we've got like one lead here and another lead out here. We apply positive voltage, and there's some current running through it. Which means that according to the right-hand rule, let's see, boop, so the magnetic field would be going through the loop, and looking from the side here, if that was our positive voltage, this was our current, the magnetic field lines would go something like that. So how does this change the attitude of our spacecraft? It's just a wire with some magnetic field you're running through it. But remember, when we went over the magnetometers, just going to scroll down here, the Earth has a magnetic field too. Now, whenever you have two magnetic fields that aren't quite lined up with one another, so say we've got one magnetic field here, B1, and then B2, there's some angle theta between them, they experience a force, and they want to try and line up with one another. Now you can kind of try this out with regular magnets. When you stick them close together, they want to snap together, right? They want to align their fields with one another. And the same goes for magnetic fields generated by the Earth and magnetic fields generated by the magnetorquers. So as your spacecraft is moving through its orbit, if you've got your magnetorquer powered, it always wants to try, it'll apply some force to try and align itself with the direction of the Earth's magnetic field while you're in orbit. So the advantages of this is, because if your orbit is stable, and you're going through that orbit day after day after day, you will begin to align yourself with the direction of that field. Especially if you are tumbling, or say you've dispensed from whatever dispenser that you're shoving a CubeSat out of, and you're like tumbling through space, really erratic, really chaotic attitude shifts, where other active control systems like thrusters have to go like, ah, crap, where am I pointing, where do I have to actuate these thrusters really quickly? They just can't keep up with that. What magnetorquers do is you can just flip them on and just wait, because what it does is it applies a stabilizing torque to your craft, like if you're spinning erratically, and over time it'll just start to slow down to the point where you can go like, okay, magnetorquers off, active control systems on. It's gotten to the point where other active control systems can reasonably control your attitude and stabilize it and do whatever you want. So oftentimes magnetorquers are used to detumble the craft. So magnetorquers function detumble. So if you can't actively control it with other systems and you just want to slow it down a little bit, enough for other active control systems maybe down the road to take over, just switch on your magnetorquers and let it be, which is a really nice thing. The downside is that they generate significant magnetic fields within your space vehicle. Now, depending on if you've got large currents or other components that use large currents running through your space vehicle, that might damage some equipment, electrical equipment on board, or it might mess up your sensors. Like, remember before, if we have magnetometers on board and we are measuring the Earth, trying to measure the Earth's magnetic field, it's kind of really hard to hear someone like whispering to you when it's kind of like someone trying to whisper to you in the middle of a rock concert, right? If the magnetorquers were the rock concert and the Earth's magnetic field was the whisper, right? You've got this thing blaring right next to you while you're trying to like focus on this thing that's very ephemeral compared to the magnetorquers. So you kind of keep that in mind when you're designing these systems. So yeah, we've got thrusters, we've got magnetorquers. Another way of passively controlling your attitude is something with, oops, it's still green, is gravitational gradient. So this one's a little bit more complicated, but it's not too hard to get a grasp of. So the way the Earth's magnetic force, the way the Earth's gravitational force works is it decreases the further out you go. Basically, exponentially decreases the further out you go, away from the Earth you go. So if this is your radius, and this is the force of gravity, and this is the radius of the Earth. So if I'm inside the Earth, it's actually linear. That there are proofs online. You can go look why that is. And it increases as you get to the Earth's surface. And as you hit the Earth's surface, you have a maximum gravitational force experienced that exponentially decreases as you go away from the Earth. So what the gravitational gradient is the change in force with relationship to distance, right? So if I had an infinitely long, just go like infinitely long rod in orbit. Actually, I'll make this smaller. Say we've got the Earth here. And we've got this infinitely long rod in orbit around the Earth. Right, that goes on until infinity. This part of the rod here will be experiencing way more force than the rod out here, than the portion of the rod out here, right? Both are pointed, so if, looking at the top side now, oop, still red. Looking from the top side now, let's try and orient this perpendicular, or let's, so let's see if our rod was in this orientation, and this goes off until infinity. This part of the rod experiences way more force, way more gravitational force than this part of the rod because it's closer to the Earth, right? So imagine our rod being on this graph here. So this one is experiencing much higher force than the part out here, which should be in red. So what that does is if they're both of these forces are pointing towards the Earth's center, this one's kind of tiny, right? If both of these forces are pointing towards the Earth's center, this one's really big. This force that's close to the Earth is really big. This force that's far away from the Earth is really small. What'll happen is you actually get, and draw a bit of a moat. You have a big force here and a small force here. What you get is you actually get a bit of a moment about your craft. So let's, all right. So you actually start to spin your craft. Ooh, I'm getting lag. Actually start to spin your craft about its axis, right? So what you can do, and what that'll do is it'll eventually stabilize out to where you've got this infinitely long rod pointing radially away from the Earth, because now, oh, come on. Okay. Because now you've got the big force and the small force lined up with one another. So once they're lined up with one another, there's no difference anymore. They don't apply a moment anymore. There's no more moment. Which just so happens to be when that infinitely long rod is lined up radially with the Earth. And what you can do is that you can kind of use that tiny force differential along the length of your space vehicle to shift your attitude ever so slightly in orbit. It's not an active control measurement, and sometimes you don't really want it at all. So like if you wanted to look at something else or wanted to like look at, say, another satellite in a network, you don't really want to be pointing in the way that the gravitational gradient is kind of nudging your spacecraft in. So you might have active control systems that try and fight against that. But it's something that exists regardless of whether you build that in, and you can take an advantage of that if you so choose. So, alrighty. So that's kind of more of the passive control systems that we have available. Now, more active things would be something like reaction wheels. So reaction wheels kind of work similar to the way that control moment gyros work, except that the way that they work by using conservation of angular momentum is you have this disk, right? And it has a certain rotational inertia. And say you're in orbit and you spin up that disk inside the space vehicle, your space vehicle is actually going to spin in the other direction, right? Because conservation of angular momentum, at the onset, neither of them are spinning. You start spinning up the disk in one direction, your satellite will spin up in the other direction. Now what you can do is, again, similarly to the way that control moment gyros are oriented, you can have them in an orthogonal layout or tetrahedral layout, and you can have one on each of these axes with different speeds. So what you can do is you can actively control the speeds of each of these wheels to control your rotation in all three axes. So I wanted those axes being roll, pitch, and yaw. So in this case, so roll would be if you've got a little airplane here. Roll would be that. Roll. So roll, pitch, and yaw. So pitch is the up and down, roll is the side to side, or it's a bit hard to describe. Roll is the, hang on, I can do this with a ball. So if this is our control ball and we're looking directly at it, roll is this direction, pitch is this direction, and yaw is this direction. So, and in the center there we've got our little airplane. So if I was rolling, I'd be going side to side. If I was pitching, I'd be going back and forth. And if I was yawing, I'd be going side to side. So you can control, with reaction wheels, you have active control of all three axes. Again, similarly to how control moment gyros can be laid out in tetrahedral to add some redundancy to the system, so too can you put reaction wheels in a tetrahedral orientation, because if one fails or is saturated, and I'll get to that in a little bit, you can have three other reaction wheels define a 3D, fully control a 3D, your 3D vector, 3D attitude vector. So I mentioned saturation. So what the hell is saturation? So a reaction wheel has a maximum speed, right? If you take one reaction wheel, you spin it up to its maximum speed, you are spinning in the opposite, your space vehicle is spinning in the opposite direction at the maximum possible speed that you can spin along that axis, right? There's nothing, if you don't have any other control systems on board, and you're in deep space and you don't have gravitational gradient, you don't have any solar wind or anything like that, There's nothing that will change your attitude aside from this reaction wheel. And you spin it up along that axis to its maximum speed. You are spinning in the opposite direction along that axis at the maximum possible speed that you can. You cannot go any faster. So what happens if you want to go faster? Well, you can't really do that. You have to have another system on board. And what's more is that that reaction wheel can't spin any faster in that direction, which means that you can't control the attitude anymore along that axis because it's spinning as fast as it possibly can, which is what we call saturation. So if you have, so say you wanted to spin in a certain direction, right? But you also wanted to pitch, and you also wanted to change, make micro adjustments to your speed, sometimes a little bit faster, sometimes a little bit slower. You couldn't do that anymore because your reaction would be saturated. You couldn't go any faster. You could go slower, you could slow it down a little bit along that axis, but you couldn't go any faster. One thing that you can do is you can desaturate your reaction wheels. So what that means is you can slow down that reaction wheel and then compensate that angular velocity with another system or another reaction wheel, or in this case, if you're in a tetrahedral orientation, another pair of reaction wheels. So if this reaction wheel is saturated, I can use components of the other three to speed up a certain degree and then have this one slow down a certain degree, and I will maintain my angular velocity. And then what I can do is, okay, but I want to speed up again, so I'll re-speed up that slowed down reaction wheel to get even more of a boost in that direction. Now, it's often not done. You're not often desaturating reaction wheels with other reaction wheels, because if you're going as fast as you possibly can, you don't want to, compensate for that by speeding up your other reaction wheels to go faster in a certain direction. It is done, but not on a permanent basis. It's basically more often used in tracking of different targets. So if you're like looking at something on the Earth and it's moving really, really fast, or something like that, your tiny little reaction wheels can't go that fast. The reaction wheel that's in its primary direction will spin as fast as possible, and the other, if you're in a tetrahedral, the other three will go like, oh crap, we need to move faster, and give it a little bit of an extra boost to help the tracking of that target. But what's more often done is, say you have a reaction wheel, and it's spinning at omega max. It's spinning at its maximum velocity. What you can do is you can have, just going to draw a little our satellite here, our little 3U box CubeSat. What you can do is you have a certain, you're at omega max. But you also have thrusters. Say you have some thrusters on board. Well, hey, that's convenient. What we can do is we can spin up in the direction that we want to keep spinning while slowing down the reaction wheel, such that the changes in our angular velocity remain constant. So we're not actually speeding up along our axis, we're not slowing down, we're using the thrusters to compensate our angular velocity decrease from us slowing down the reaction wheel. And what that does is now we are still at our, so looking from the top now, we're still at our same velocity. So let's start from the beginning. This is our reaction wheel, it's at omega max, and we'd be spinning the other direction. It's at omega max, we'd be spinning the other direction at our omega max. Omega satellite max. And we use our thrusters, so say we've got our thrusters here and here, to speed up along this direction, in this, or along that axis. So we spit out our fuel to speed up in that direction, but we slow down our reaction wheel so that our omega remains the same. but our reaction wheel is going a lot slower. Our reaction wheel is going a lot slower, which means that, hey, we can speed that reaction wheel up again to get even faster angular velocities. But the real reason that we do this is desaturating with propellant systems is because reaction wheels are far more precise method of attitude control, because we can have encoders or other measurement devices that can really finely tune the attitude that we are, or the angular velocity that we are rotating the space vehicle at, which makes reaction wheels a really good way of precisely controlling our attitude, whereas thrusters aren't so precise. They tend to be, they can give a lot of thrust and give you really big angular velocity changes, but they aren't. The trade-off for that is they're not as precise. It's a lot harder to determine how long you need to open the nozzles for, and even then sometimes other stuff happens. So what you can do is you can use your thruster systems to desaturate your reaction wheels such that you can have the angular velocity that you want, but also have the fine control of the reaction wheels back. So that's kind of the reason why you want to desaturate your reaction wheels. A good example of this in real life would be the Parker Solar Probe, where they were orbiting the sun, and their perigee got really close to the sun, so they're really whipping around that thing stupidly fast, but the Parker Solar Probe wanted to look at the sun, right, because it's a solar observer, it's a solar probe. So we'd have the sun in here. Oh, it's a terrible shade of yellow, but we're going to go with it. That's really hard to see. I'll put it in purple. Put it in purple. Sun's purple for some reason today. And their orbit was really eccentric, so they'd get really close to the sun and really far away. So their velocity right here is stupidly huge. I'm going to put this in a giant V, right? Which means that they have to shift if they want to look at the sun, they've got to shift their attitude really fast, right? They've got to have a really fast angular velocity at that point in their orbit. So what they would do is they'd use their thruster systems to actively desaturate their reaction wheels every orbit because they wanted fine control to be able to look at different spots in the sun, but they also need to have really high angular velocities. And remember, as I said before in our example, if you wanted to keep looking at the sun, you'd have to slow down your angular velocity here and speed up here. So the difference in your maximum and minimum angular velocities is huge in this case. So you're going to have to do a lot of desaturation, and that's what they did. They used onboard propellant systems to desaturate the reaction wheels so that they would have fine control while they're at the closest to the sun to be able to observe it as closely and as accurately as possible. But still have the ability to have high angular velocities. So yeah, that's kind of an example. Oh, did I not write? Oh, it's detumble. So that's a good example of different methods of attitude control that you can put on your space vehicle. Whether it be spin stabilization, which is kind of a passive method, or thrusters, which is an active, gravitational gradient, which is a passive, or magnet torquers, which are semi-passive. I mean, you just turn them on, they kind of do their thing, or reaction wheels, which are active. So yeah, so that kind of covers what we have for, okay, it's just loading in, for attitude determination control. Going back to our list here, next we're going to cover a bit of thermal control systems. So if we take, hang on, I've got to move my notes. So what is the purpose of a thermal control system in a space vehicle? The purpose or function of a thermal control system on a space vehicle is primarily there to make sure everything stays at an operable temperature. Now, what do I mean by that? Well, electronics have an operable temperature range, right? If you make a circuit board too hot, the components won't be able to work as efficiently or at all. Same with optical systems. So if you have lenses on your optic system, or you have your focal plane array, you heat those up too much, you're going to get self-emissivity, and the images that you get off of that are going to be absolute crap. Or loss of focus and all sorts of other weird stuff. So you want to keep things within a relatively tolerable temperature range. So some components that do that would be would be things like radiators. So you can actually, I'll take this again, kind of like attitude determination control systems. You can have more passive, you can have passive or active control systems. So for passive, we have things like radiators. Radiators, ablation devices, but those are very temporary and they're not used often. But for the most part, we're just going to stick with radiators. For active control systems, you would have things that or mechanisms that work with a coolant, so there would be things like cryocoolers. So different devices that work off the Brayton thermodynamic cycle, or a bunch of different other ones. I'll post a link down below if you want to look more into how cryocoolers and their different thermodynamic properties and cycles that they work through to achieve really, really cold temperatures. So radiators work in a in a very simple way. They just basically increase the thermal emissivity of your spacecraft. Because remember, I'll just kind of give you a crash course of heat transfer. There are three primary methods with which you can conduct heat off of or into a system. You have conduction, convection, or radiation. Now, if you're trying to take heat away from your satellite, I'll give you a quick description of each of these. So conduction is basically when you're touching something. So I'm touching the wall over here. My skin is hotter than the wall surface. The molecules interact, and heat, or thermodynamic heat, is exchanged between me and the wall. Heat flows out of my hand into the wall. So it's touching stuff. Convection is kind of similar in some ways. It's fluid flow passing over an object. So anytime I am within a fluid and I am like waving my arms around, based on certain properties of a fluid, how fast it's going, etc., etc., you will either add heat or take away heat from your system. It's very similar to the prospect of a radiator on a car. You notice how they're always on the front, and that's because as you're driving your car, you're taking air that's coming in from the front of the car and flowing it over the radiator, thereby cooling off the coolant within the radiator. So that is fluid flow. Fluid flow. And you also might have heard this term used in convection ovens, where they take a hot fluid and they flow it over whatever it is you're cooking in the oven, thereby transferring heat into whatever you're cooking. And yeah. Radiation, which shouldn't be happening in your oven, well, actually it does. I am joking. Radiation is the thermal emissivity of photons or other energetic electromagnetic waves from every object. Like if you've ever seen people through an infrared camera or something like that, we look like we're glowing. That's not because the camera is like mapping pixels to living things. No, it's because everything that has thermal energy or heat or is at any certain temperature, they give off a certain amount of radiation that goes into things like black body radiation and whatnot. So anything that's not at absolute zero will be emitting some sort of light at some sort of frequency. So that's so just as you can transfer heat away from yourself by giving off light or electromagnetic waves, you can also absorb thermal energy through electromagnetic waves. So something like the sun heating up or giving its energy to plants, and they go through their own chemical cycles where they use the where they use the electromagnetic energy from the sun to convert that into chemical energy. So radiation can go both ways. You can heat things up, you can cool things down, and the way radiators work on satellites is they change the emissivity or they increase the emissivity of your satellite, making it so that you give off a lot more of this electromagnetic radiation. Now, you might be saying like, well, why can't you? That doesn't sound very efficient, because in some cases it's not nearly as good as giving away heat as something like convection. But that's because we don't really have an atmosphere to deal with in space, right? I mean, we can't touch something else in space. You're just the space vehicle. You're just the satellite. There's nothing else to touch to transfer heat onto, unless you have this like massive block of like zinc or something that you want to cool yourself off on. But then again, over time, the zinc will actually heat up because you're pumping energy into it over and over. And it's really expensive to get a gigantic block of zinc into orbit. So there isn't really anything to touch to cool yourself off. There's no atmosphere or other fluid flow to cool yourself off of. So you're kind of stuck with radiation as your only method of giving off heat. So a lot of the different systems in some way, a lot of the different thermal systems on board a space vehicle in some way revolve around losing heat through radiation in some form or another. So with radiators, that just increases your thermal emissivity, makes it so that you give off more heat by electromagnetic radiation. Now the downside thing is with those sorts of radiators is that it makes it very easy. So if you're like scanning the night sky or something like that, and you knew the thermal signatures of the satellite, it makes it really easy to find your satellite. I mean, it's kind of easy to find it out based on launch points and whatever. But if you didn't want anyone to know that your satellite was there, you might want to be careful about how your satellite emits heat and where. So you might want to have it on different parts of the satellite or whatnot. Active heating systems like cryocoolers actively pull heat away and pump it into a radiator. So what they're basically doing is you take, say, the object you want to cool, you have your cryocooler that's with your fluid flowing through it, and you have a hot sink, which is a radiator, and you're just basically pumping heat into this thing. So it takes energy to pump heat in and out of a working fluid, and you're just basically increasing the temperature of this radiator to stupid degrees, which the higher your temperature of something is, the more heat it will radiate out through electromagnetic waves. You can see this if you've ever seen like people stick metal into a forge or something like that, and they pull it out and it's like yellow hot or something like that. At that point, the metal has reached a temperature where it has started to glow in the visible spectrum. So you're starting to actually see, your eyes are able to actually see the the electromagnetic radiation that's coming off of that object. That's kind of what it's doing with a cryocooler. It's pulling heat away from something and just pumping it into this heat sink so that it really gives off a lot of heat, as much heat as possible. So places where you'd want to use a cryocooler would be something that must actively be its temperature must actively be maintained and controlled. So this isn't usually typical for something like onboard systems where they have a very, or at least a marginal tolerance range for their temperature. They don't really care necessarily about being a specific temperature, they just want to stay within a range. Where cryocoolers are more often used is, as before mentioned, with optics and optical equipment and focal planes for like capturing light, because they often operate at a very specific temperature. So different focus mirrors, if they're not at the right temperature, might be warped slightly out of shape, so they don't focus the image to quite the degree that you want it to. Same with your focal plane array. If it's not at the right temperature, it might be self-emissive, so it's generating its own electromagnetic radiation just because it's at a certain temperature that's above 0 Kelvin. And so it might be collecting that information, but that's not the image you want to collect. I don't care what self-emissive stuff the focal plane array is capturing. I want to look at what I want to look at. So that's one thing those are typically systems that need to be actively controlled. Most onboard systems don't need that sort of active control, and can do just with the radiators. They don't need active systems. So that's kind of what they do. Different requirements. I mean, the requirements you might see on thermal control systems are fairly standard. So I'm going to say you've got your regular control requirements if it's an active control systems. If it's an active control, so things like rising time, overshoot, steady state error, and all sorts of requirements that are associated with the design of the control system that you're working with. As far as thermal control systems that are passive, you would have emissivity requirements, so able to give off a certain amount of heat in a certain amount of time, and you'll tune this to whatever, which are typically bound to the temperature. Which are typically bound to the temperature tolerances of any onboard equipment that you have. Oh, that's behind the camera. Sorry about that. So it's if you want to give off heat with your radiators, well, the driving factor behind that is the desire for everything on your space vehicle to work properly. You don't need, I mean, aside from the satellite's function, you don't really care what temperature it's at unless you're trying to look at imaging and your self-emissions, start to get in the way. So you're just, for most thermal systems, you just want to be able to maintain temperature within a certain tolerance, because ostensibly all the electronics on board will be generating their own heat through electrical resistance. As you're passing a current through, there's minor electrical resistance that goes on. It generates some heat, which you want to whisk away. And also, while you're in the view of the sun, it's giving its energy, it's radiating its energy onto you, which you are absorbing not only in your solar panels if you have them,
which is being converted into electrical energy, but also on the satellite's surface itself, which is then conducting down to all your electrical components. So you want to make sure that the sun's radiation isn't going to provide a problem and exceed the tolerances that you set for temperature for all your onboard systems. So you might want to have a radiator or something that can handle pulling heat off the satellite in direct view of the sun, or at least pull off enough of it so that it doesn't, fry while it's in direct view of the sun for a certain period of time. So yeah, that kind of goes over a general overview of all of the systems that you might see on the bus. Again, as I mentioned before, the payloads can have very different things depending on what you're trying to do, so I'm not going to be covering that in this video. So the last one we're going to be talking about is communications. And again, as I mentioned earlier, if you are using if you have a communications payload, you won't necessarily have a communications system on your bus. If you're sometimes yes, sometimes no. Sometimes you might have communications payload and communications on your bus. So like if you want to do tasking and commanding of the space vehicle from your bus to your payload, it all depends on how you want to manage the informational flow through your space vehicle. So communication comms. Oh, what's no, go away. Alright, so communication. So communication is largely done through electromagnetic radiation, usually radio waves. And this kind of pairs into your attitude control system, so you can have omnidirectional or directional antenna. So, in large part, the way a communication system works is you have a collection or transmission device. I'm just going to draw like a kind of general dish. So you have a collection/transmission device, which goes into your electrical systems, where it is then processed. So if you have a certain package structure or a communications protocol that you're using, so you have electromagnetic waves that are modulated at a certain frequency or a certain amplitude, so that goes into things like AM or FM. So AM standing for amplitude modulation. So an AM wave would look something like, so that would be amplitude modulation. You're changing the amplitude of your signal over time to display information within that wave, or you're changing the frequency modulation. So you have high frequency, low frequency, high frequency, low frequency to display information within within those electromagnetic or radio waves. So typically you have your collection device that goes into your computer, which then unpacks and decodes the data that you have. You can also have additional layers of communication on top of this, like encryption or other protocols. And what they say, I don't want to get too much into the Fourier transforms and frequency decomposition, but the large and short of it is, you take your radio waves, you encode that into digital data, and then from that digital data, you read what message is trying to be sent. and that kind of works both ways. You can transmit or you can receive. So in large part, it's just, yeah, that's what it is. There are specific bands and specific protocols that are used for satellite communication, because we run into different issues with communication in space than we do with communication on the ground, namely the atmosphere. So if we have the Earth's surface here, we have the atmosphere above it, and then we have our satellite, which wants to communicate to ground, right? Wants to communicate, actually, it's not sending its radio waves at a person, it's sending its radio waves to a ground station, right? We want to be able to send communication between the satellite and a ground station. Well, the thing is that specific frequencies are absorbed by our atmosphere. So certain frequencies might not even make it all the way to ground. They don't get all the way there. Some frequencies might lose attenuation, so they might be very weak when they hit the ground, or sometimes they just reflect off. So depending on what kind of frequencies you're using, you want to make sure that you have good ground attenuation if you're communicating to ground, and and you aren't losing a lot of your signal. That being said, there are different bands out there that are commonly used, so that would be things like different frequency bands that are used. There are things like S-band or X-band, which have different bandwidths, and you can send different throughputs of data through each of those. Those are regulated, so you can look. I'll post a link down below to some of the documentation for communications regulation with regards to satellites. Now, between communication to ground and your satellite, you can also have inter-satellite communications where you don't have things like the atmosphere in the way. So that'd be like something from satellite to satellite. Now, why would you want to do this? Well, satellite to satellite. Now, why would you want to do this? Well, sometimes you have, say that's the Earth. You have one satellite that's looking at one part of the Earth. Say you want to communicate with a person that's all the way across the globe. So, say you're here, and someone else is over here. Well, this satellite doesn't actually have view. This satellite doesn't have visible line of sight to the person you want to talk to. So it'll have to go through like, hey, I want to send my message to this satellite, which does have line of sight view. And what we can do is we can send a message to this satellite, which will send it to this satellite, which will send it to our recipient. So that'd be like communications relay. An example of that would be something like the Marco A and Marco B cube satellites that were sent with the InSight landers. What they did was they relayed image information off of the InSight lander. So the InSight landers send information to the CubeSats, and the CubeSats would send it back to Earth, because that didn't as they did it as more of a proof of concept than out of necessity, because the InSight lander actually did have enough communications capability to send data to Earth, but they just basically proved that yes, you can use Cube satellites for deep space communications relay purposes, which is huge. So things like Elon Musk's Starlink, it's kind of this idea where you have a bunch of these satellites in network with one another, and you can send information up over to whatever person you want to talk it to, and then back down again. More often what will happen in today's satellite networks is, like, say you don't have ground connection, like to internet or a phone line or something like that, it'll send information up to a satellite, and that satellite will go like, hey, we have this remote ground station right here, let's send it down to that, and then they connect over wire to another person. So it's more for a remote access thing than purely communicating through satellites. So yeah, that's the purpose of that's kind of the purpose of communications. It's to communicate a function to transfer information. Between one satellite and another. Now, the kind of requirements you might see off of these sorts of systems would be things like data transfer rate, data transfer rates, maybe availability. So if your satellite can only point in one direction at a time and can only communicate with one person at a time, you might have some requirements that say, yeah, you've got to cover, be able to link with so and so many people at the same time. You might also see more like protocol related requirements or encryption requirements. So you've got to send your bits with a certain level of encryption, or using this method, or communicate along, or communicate along certain bands. So those are the kind of requirements you might see on communication systems. Generally, they're also tacked in are interfacing requirements with other systems. So say you've got two different kinds of ground stations that run different software on them, and you have a requirement that says, yeah, I want you to be able to communicate with this system and this system. So you kind of have to tailor your space vehicle to be able to work with that. So yeah, those are the kind of requirements you might see on communication systems. I'll post a link down below with all of the stuff related to that. But that, I think, covers about it for onboard systems, general overview of energy and power systems, power generation and storage, attitude determination and control systems. So different methods of determining your attitude, whether they be magnetometers or control moment gyros, and different methods of control like reaction wheels or thrusters. Your different thermal controls, whether that be passive or active, like cryocooler, passive like radiators or active like cryocoolers, and different communication systems which use directional or omnidirectional or directional antennas to take in electromagnetic radiation, decode that information into digital data that you can use. And then process that data as you see fit, or transmit that data to ground stations so that they can process the data that you send. So yeah, that covers about it for beginner introduction to space vehicles. I hope you enjoyed the video. It'll be me signing off. Good night.